So graphing linear functions, well, we already know how to graph points. Now we got to graph actually, and when we say linear, by the way, we're talking about straight lines on this. So even though I did show on that last example some curvy lines, we should only see straight lines on these. All right, points and equations. Now remember, in an ordered pair, you got the parentheses, and then you'd have an x value, and then you'd have a comma, then the y value. And that would close the parentheses. Something like this. So the x and y values in an ordered pair need to make whatever the equation is true, right? So I think we saw the 2x before when we did the machine example, or I guess it's the function example, right? So for example, and we did see this, 2, 4 would work. 2, 4. That would be a point that would make this equation true, right? Because the x is 2, the y is 4. Yes, that would make a true statement. Just like we've seen when we check our equations when we were solving one variable equations, right? And I think, I know we saw a different value. I can't remember if it's 3, 6, but 3, 6 would make this work, okay? And how many values would make this a true statement? There's an infinite number of values, okay? Which is why on a graph, it's nice to just show the line, because the line indicates the pattern of values that would make the original equation, in this case, y equals 2x, true. Even if it was shown in function notation, so if it was like f of x equals 2x, the same thing, these ordered pairs make the function true because it makes the equation true as well. Similar to solutions, yeah, but now with 2 values. So now there's 2 values that will make an equation true. And we have to be able to show that on the graph. So before, when we had equations with one variable, only one value usually made it true, unless some of the unique scenarios where it was all real numbers or even no solutions, right? But now we're going to see that there's going to be an infinite number of ordered pairs to make these true, and we'll see that again on a graph. We just have to determine if these 2 ordered pairs will make the equation true, okay? Do remember that it's always x value and then y value. Some students like to show it with x and y above like this, and that's fine. But again, I guess I need this equation. Y equals, I guess that's negative 3/4 x, sorry about that, plus 8. And what does it tell us in that first ordered pair? It says that the x value is 4 and the y value is 5. So let's get those in there. X value is 4. And the y value is 5. Now, is it a solution? Is it a solution to the equation? Again, remember when we checked, we put a question mark over the equal sign? That's what I'm going to do. So you could put this in the calculator if you'd like. I'll evaluate it real quick. But negative 3/4 times 4 is negative 3. And then I would add 8 right there, and negative 3 plus 8 is 5. Now, we already had 5 equals, right? So that would be 5 here and here. Just kind of expanding there, but 5 equals 5, yeah, that's true. That would be true right there. So that means that what points are solutions? This one is. I'm putting a check mark there. I'm not, you could put yes, I guess, but check mark seems to be a universal sign of okie dokie, all right? Okay, so what about the next ordered pairs? Let's get rid of some of this stuff. All right, so this one, x value is negative 16, and the y value is 21. Let's see if this is true. There's my question mark over the equal sign. Negative 3/4 times negative 16, it's going to be positive 12, and then plus 8, which I know is 20. Your calculator knows that too if you need it. Then we say 21 equals 20. No, that's false. So this one will say, I just cross it out. I believe on the homework it's just yes or no, or true or false, something like that. Now this process, you may think, well, what's the point of this? It's because in the future when we start to put these on graphs, we only want to put on the graph the true statement ordered pairs. And not only that, but in the future, they're not going to give us any ordered pairs at all. We have to test our own values into the equation. For the most part, we usually start putting x values in, but we'll see some scenarios where it's nice to put in y values as well. Now, there's some values that are very convenient to put in as well, and then we'll want to know what those are. Usually 0 is a very convenient value to use, and we'll talk more about that here in a second. 1s are nice values to use, but again, sometimes it's just not, I guess it's not handy to use a 1. So you have to use 2 or 5 or 10 or some other value. We want something to fit on the graph, especially the ones that are going to be on the homework, and we can kind of force that to happen. All right, this one's written just a little different. This is what we call standard form for a linear equation. Not that I think you care, but well, let's go ahead and rewrite this then and start plugging in some values. Negative 5x plus 9y, this should equal negative 20, right? If it's true, then it is a solution to the equation. And right off the bat, they say x is 0 and the y is 9. Remember those 0 values, right? Sorry, that should be a y right there. There we go. All right, so I replace the x with 0 and the y with 9. Let's go ahead and do that. X is 0 and the y is 9. Some of you, I think, can do this in your head, and that, if you can, that's great. Negative 5 times 0 is 0. 9 times 9 is 81. So 0 plus 81 equals, I forgot my question mark, didn't I? There it is. No, that's not going to be, we can just make that really a phantom 0 right there. Yeah, that's false. Okay, so I'll go back to the two ordered pairs they gave us. This one's not going to, that's not true. That's not going to make the equation true. Okay, so what does that mean on the graph? So if I were to put this on a graph, let's see if I can kind of demonstrate this x and y's, right? So the graph for this one, 5 ninths, 5 ninths on negative 20b, maybe, I don't know, something like this, okay? It's saying that if you graphed 0, 9, which would be probably, I guess, up here, right? See, it's not actually on that orange line that I drew. Meaning that that purple point that I just put on the graph, it would make it a false statement. That's why I did make it a false statement, okay? So graphically, that's what it means. But let's go to the second ordered pair here. And we got a x value that's 4 and a y value now that's 0. So let's clean some of this garbage up. The x value is 4, the y value is 0 now. Well, negative 5 times 4 is negative 20. 9 times 0 is 0. That's nice, because negative 20 does actually equal negative 20. This is true. So where is that? 4, 0? Yeah, that'd be this point right here, okay? See, but it lands directly on that line, okay? So this one, again, I'll put a check mark there to indicate that it is a solution to the original equation right there. So on this one, it says, hey, we got to complete these ordered pairs, but they've given us these values. Again, I'll point this out. In the future, they will not give you any values. You'll have to determine your own values to put into the equation, all right? But to start out here, this one says that the y value is 0. Okay, so let's go and write this out. Negative 8x plus 6y equals negative 24. And just right now, I'm going to go in and, oh man, for the left, there we go. I'm going to replace the y with now 0. This is now an equation just like we saw in Module 1 that I now need to solve for, in this case, x, right? So 6 times 0, that's a, well, I'm going to make that a phantom 0. And then I got negative 8x equals negative 24. Just divide both sides here by negative 8 to see that x would then equal 3, 3, 0, okay? And you can check both values in the original equation to make sure it's true. This will work. Okay, so let's go back and replace now for the second ordered pair x with 0. All right, so x now is 0, and yeah, that's just going to 0 this one out. So 6y equals negative 24. Just to save me a little space here, divide both sides by 6 to make that a phantom 1. Y equals negative 4. So 0, negative 4 would be this point here. And then just kind of a random y value. That's okay if it is, because we can solve that too. I guess I'll use the original one up here just to save some space and time. But 6 times negative 3, that'd be negative 18. Maybe I shouldn't have done that because I got to add 18 to both sides now. So plus, see, I jacked that up too. That's going to be negative 6 in any case. I'll write it down here. Negative 6 equals negative 8x. Divide both sides by negative 8. Get a fraction on this, that's okay. Yeah, it shows x equals 3/4 right there. Just kind of pressed for time. Sorry about that. Positive 3/4 it looks like. and I'm doing that a little fast, so if I made a mistake, I do apologize. But this, even though this is a fraction, that's okay, and we wouldn't want to graph this as an ordered pair, we would want these ones. Now, these two values that we just found, the first two, are unique because of the zeros. And I guess I kind of showed it on the last one with the graph. When you see on this first one, 3, 0, when the y value is 0, we call that an x-intercept. Why the x-intercept? Because if you were to graph this on a line, it would go, that's where it would be on the x-axis, okay? So hopefully you can kind of tell what that second one would be. That's the y-intercept because it would be on the y-axis, y-intercept. All right, x-intercept, y-intercept, boom. Now, the reason why these are important is because when you're graphing a straight line, all you need is 2 points. And the reason why we want these specifically is because they have zeros. And zeros make calculating very easy, whether you're using addition, subtraction, multiplication, or division, unless it's the denominator, okay? So we want to see those. And again, just think about this on a graph. So not that my graphs are pretty or anything, but that's not the worst I've ever done. So x and y, like this, right? So 3, 0, we'll say is right here. 0, -4. That's good enough to make a straight line. See that? Now, my recommendation is always to have a third point, just to make sure it's true. So like 3/4 of -3, see that'd be about right there. I know it's not proportional, but I don't care. I'm just trying to illustrate that third point is nice to confirm it. And I'll point this out again. The green line represents all the solutions for this specific equation. And so all 3 points are on the line because they represent solutions to the equation. Okay? Maybe that's more redundant than it needs to be. There's our x and y-intercept stuff. So the y-intercept is where the x value is 0. I guess that's one of the key points right there. X value 0. And then if you're looking for the x-intercept, then your y value is 0. And hopefully, again, that makes sense because there are 2 number lines, right? So if you looked at the y-intercept first, this is the y number line, but that would mean that it goes through the y-axis, which means the x value has to be 0, which is along this road or street, if you want to think about it as a map, okay? Where the x-intercept, so that's the y around the space. I'll put the x over here. That's where the y value is 0 along this line too, and that's where the lines will cross, somewhere here maybe, and then perhaps right here, something like that, okay? All right, now we got to find our own x and y intercepts, but since they are the intercepts, they are actually indirectly giving us specific values. I'm going to start with the x-intercept. Let's put x-intercept like this, kind of abbreviating there. And in the x-intercept, the y value is 0, okay, because it has no up or down value. It's on the x-axis. So that means I need to go into the equation, 6x minus 5y equals -30, and replace the y with 0. Right there. So that's, again, that kind of just zeroes that out. Divide both sides by 6. We get x equals -5. So that would be -5, 0 as the x-intercept. And then for the y-intercept, the x value now will be 0. Okay, so let's go back to the equation. 6x minus 5y equals -30. But replace the x now with 0. That does zero that out. I got to divide both sides by -5. And I get y equals 6 on this. So 0, 6 would be the y-intercept. That's the 2 answers we want. Do keep in mind that these are ordered pairs. So if it ever asks for a y-intercept, even on an exam, you have to show it as an ordered pair like this. Because if it's not shown like that on an exam, I'd have to take a point off. Okay. The reason why that's important is because we'll look at a different form for linear equations, and the y-intercept specifically is very prominent in that equation. Let's go and find the x and y-intercepts of this equation, and I'm going to start with the x-intercept. So let's put this out, and remember, for your x-intercept, automatically, right off the bat, your y value will be a 0. Okay. So we take the equation y equals -5x plus 3, and we just replace the y value that we just found in that ordered pair there to be 0, right? Because if the y value is 0, its corresponding x value should then make this a true statement. So in solving this equation, just some principles of equality here is first thing I do is subtract 3 from both sides, making this negative 3 equals now just negative 5x because our positive 3 did 0 out. And then finally we would divide both sides here by negative 5 to make the coefficient of x a phantom 1. So x then would equal, put that in the calculator, you get positive 3/5 there. So the x-intercept would be 3/5 0. And yeah, it'd be kind of difficult to graph a fractional or decimal value, so it's not really one we'd be looking to put on a graph. But then finally, the last thing we need here is the y-intercept, which again, the unique thing about that, just in terms of ordered pairs, is that the x value now is 0. So we take the same equation, y equals negative 5x plus 3, and we now replace the x, because that's the x value in the ordered pair there, with 0. Now in this format, this makes solving for the y-intercept very easy, because we can see here that 5 times 0 is 0, and then I would just simplify this into y equals, I mean, you could put 0 plus 3, but really I'd make that a phantom 0 and write y equals 3. Okay, so then of course our y-intercept is still an ordered pair, so we need to show it as an ordered pair here, 0, 3. Now we have the x-intercept and the y-intercept together. This will do. It's a nice start, right? So there's our x-axis and y-axis. I'll label it myself. Let's go ahead and put these ordered pairs on the number line. There's my x-intercept at 4, 0, so 4, 0 about right here. And then 0, negative 3, again is 0, and then down 3 would be right here. That's good enough, again, to make this line go through the ordered pairs. Now something just happened right there, an interesting phenomenon, because I'm doing this by hand, but I missed that purple point right there, okay? Now we know how technical math people are, and I'm one of them, okay? So we gotta fix this. And the question is, how do we fix it? I just make the point bigger. That's the graph right there. And when you're doing it by hand, I'm not looking for perfection, right? Like even if this was an exam, what I wouldn't wanna see, as big as you want to make your points, don't do something like this. Certainly not something like that, okay? We don't want to see those other 2 green lines there. We want the original one, this one, okay? All right, now we have this equation, 5x plus 4y equals 20, and we're going to fill in this table, all right? Now remember, these are all ordered pairs, -1 something, 0 something, something 0, and then 2 something. And we do have this would be the y-intercept here because the x value is 0, and this would be the x-intercept because the y value is 0 here, whatever we get there. But I'll start at the top of the table where it says the x value is -1. And so just writing out my equation here, 5x plus 4y equals 20, right? So at this point now, I can go in and replace my x value, because again, I'm looking at this first ordered pair. I just don't know what the y value is, but I know I can replace this x value with -1. And then I just use principles of equality now to solve. So I'd say, well, 5 times -1, that'd be -5, right? So still plus 4y equals 20. And then I would have to add 5 to both sides. Like this to zero that out. I'll drop my 4y, which now equals 20 plus 5 is 25. And then divide both sides by the coefficient of 4, which will then make that just a phantom 1y as 25/4. And I know some of you would probably change that into a decimal, but I'm going to keep it as its fraction form as 25/4. Okay. Now this one's kind of hard to graph. I mean, you could go to the graphing point at this time, and maybe that's even where the decimal would come in handy. That'd be 6.25. Okay. But I'm going to skip that. We can find its estimated point, but I want to find the next ordered pair here, which is the y-intercept. So I go back to the equation and I say, look, we're going to replace the x with 0 here. And that's nice because this term right here is going to be 0. So I'm really just left with 0 plus 4y equals 20. And I don't really need the 0 there, or even the plus sign right there, okay? So 4y equals 20. I divide both sides here by 4 to get y equals now 5. So that would be the y value in my y-intercept of 0, 5. Okay, so there's that ordered pair. And again, this one gave us exact values of 0 and 5. So we can go and put that on the graph. There's my purple point there, okay? Now to make a straight line, we would only need one other point, but we'll still put the other 2 points on there, or approximately on there, so that we can make sure that the pattern is consistent. Now for this next ordered pair here, this is the x-intercept because the y value is 0. So when I go into my equation, I need to replace the y there with now 0. So that's what I'll do. Let's replace that y value with 0. We're just solving this equation. Now remember, 4 times 0 is 0. So even though it would give you 5x plus 0 equals 20, I really don't want that plus 0 there, okay? So I end up with 5x equals 20, making that a phantom 0. Divide both sides by 5 now. Tells us that phantom 1x would equal 4. So I end up with 4, 0 being my x-intercept, and that would be about right there, that green spot, okay? Now we do have one final ordered pair to use here, and that's looks like where the x value is 2. So let's go in here, kind of clean this up. But yeah, now I'm going to replace that x value with a 2. Okay, so 5 times 2 is 10. And again, just by looking at the intercepts right there, you can see how that makes it so easy because we get these phantom 0 values now. But now this one is 10, so I'll have to subtract 10 from both sides, which isn't a problem, hopefully, but I'll drop this 4y, which now equals 10. And finally divide both sides by 4 to make that coefficient of phantom 1. And we end up with a y equals, that'd make 5 halves, or about 2.5 there, okay? Now again, just for mathematical purposes, I do like to see the fraction. So I'm going to show this as 2 and 5 halves like this as the ordered pair. Okay, so where would that be? Again, that's 2 and 2.5. That'd be about right there, okay? I know my point's a little bit off. And then I got the red point at -1 and 25/4, which again was about 6.25, which would be about right there, okay? So what do we get when we make a line on this thing? Well, let's find out. Okay, so I'll see if I can connect these points very well. All right, so it'd be about, I don't know, something like this. Looks like something like that. Okay, and then we get the arrows like this. All right, and that would be the graph for this equation, at least using these points. Although, again, you see that we only really needed these two, the y-intercept and the x-intercept, in order to solve this. Something like this where they're not going to give us any ordered pairs to put on the graph. We have to choose them ourselves. And again, 0 and 1 usually are very, very nice values to work with. If we see a fraction, then we'll want to use even more specific values, but right now we want to stick with like 0s and 1s. Now they'd usually say, you know, make a table out of this thing, and that's always a good strategy because when they're nonlinear, it makes it very, very nice, okay? Now I've got enough here for 3 points, which should do. But again, whatever value you choose is up to you. I'm going to start with x is 0. Why x is 0? I don't know, just because. But I know that by choosing an x value that's 0, it should be a y-intercept, which means it has to be on this line right here, okay? So I go to the equation. See if I can do this small enough. My 2y minus x equals 8, and I replace the x with, well, 0, right? And then I solve this for y. Now, really, I'm going to make that a phantom 0, like I'm doing, and then I'll divide both sides by 2. So that shows me that y equals 4, assuming I did my math right. So 0, 4, there's my first ordered pair. Let's put it on. I'm putting them on right now, even though you'll see me later on. I'll finish the table, and then I'll put them on. It doesn't matter, as long as we get them on at some point, okay? The next ordered pair, I'm going to make the y value 0, right here. And again, let's go back to the equation. 2y, sorry. 2y minus x equals 8. But now I'm going to replace my y value with 0. Which again, it really just means that I'm going to zero that out. I'm going to show this phantom -1 to divide both sides by -1 by. And that shows me that the corresponding x value is -8. So that gives me a -8, 0, which is now another ordered pair I can put on the graph, right? -8, 0, I found it right there. this is good enough. That's good enough for a graph, okay? But I do want to confirm it just really for my own purposes, and I'll try x is 1 right here. Do you have to do this? No, but I highly recommend that you do just to make sure you're checking your work. And so what do we get? 2y minus x equals 8. Now the x is 1 though, so there's a little bit of principles of equality here. Add 1 to both sides. That zeroes that out. 9, 2y equals 9. Divide both sides by 2. Y equals, well, 9 halves there. That's kind of ugly, but we can fit it on there. 1 and 9 halves, that'd be 4.5, right? About right there. Boom. If we draw this line like this, oh, I got it through the points too. That's not too bad. Yeah, that it looked like this, and it did, even though it covered up that orange point right there, it was there. I guess I should have put that 1 9 halves in the table, shouldn't I? There's a 2. All right, here's our next equation, and again, I'm just going to go with, especially in this format, it's always nice to use both intercepts. And so I guess I'll start with the x-intercept on this one. So yeah, we should expect that y value to be 0. So I'm going to replace the y value in this equation with 0. And again, its corresponding x value should make it a true statement, right? So this is what I get. I've replaced the y value with 0. 6x minus 3 times 0 equals 12. But remember, this whole term right here multiplied by 0 is just going to be a 0. So I'm just going to rewrite this as 6x equals 12, right? Because that term became a 0 term. Divide both sides by 6 here now. And that shows us that the x value here would be 2. With its corresponding y value, 0, right? So we end up with 2, 0. That would be about right there, 2, 0. But now what I would like is my y-intercept, which as we've seen, will make the x value a 0. So let's go back into the equation, and we're going to replace the x now with 0. So there's our full equation with the x value replaced as 0, and then we're just going to solve. But remember, since it's 6 times 0 there, it's going to be just a 0 term. Don't forget, this is not just a 3y, by the way, it's a negative 3y because of the minus sign. So when we go to divide here, we've got to divide both sides by negative 3. Otherwise, we're going to be on the wrong part of the graph there, right? So 12 divided by negative 3 is negative 4, and I end up with the y-intercept of 0, negative 4, which would be about right there, okay? And again, this is all you would really need in order to graph. You're welcome to put more points on there if you'd like, but this should be it. And then I'll put some arrows on the line there. Now, what about an equation like this one? Well, once again, I would still want to start. You can start with the y-intercept if you like. I'm just starting here with the x-intercept, which, of course, in that ordered pair would make the y value a 0. So in this equation, I replace the y value as 0. Then in solving this, we see that this term just becomes a 0. Rewriting the equation now, just simplified, negative 4x equals 0. Divide both sides by the coefficient of negative 4 tells us that x equals, well, 0. Okay, that became a phantom 1. So in doing this, the x-intercept shows 0, 0. So even if you tried to just rewrite the ordered pair for the y-intercept, just in case you didn't notice here, right, because the x value would be 0, which means its corresponding y value, we already know what happens when x is 0. The y value is 0. What does this mean? Well, both intercepts are at the origin. That's what this is, okay? Which is right smack dab in the middle of that graph, okay, right there. So that means that I can't use the two intercepts in order to graph this. I got to find another value to use in an ordered pair. So it's not going to be an intercept, just any other value. So I would say, yeah, I'd probably say y is 1. You could say x is 1 if you'd like. I think you get a fraction out of that, though, okay? So I'm going to go back into the equation and replace here the y value with 1. And then we just solve this. So negative 8 times 1 is negative 8. So now we got negative 4x minus 8 equals 0. I'd add 8 to both sides here. 0 out that minus 8 there. So that will 0 that out. I'll drop my negative 4x's, which now equals 0 plus 8 is 8. Divide both sides by the coefficient of negative 4 tells us that x now equals negative 2. So This is a negative 2, 1, which on the graph would be negative 2, 1, about right there. Okay, and yeah, that's good enough right there to make the graph. Some of you, I think, would maybe even say, well, and I've seen this before where students just kind of connect those 2 points, and that's fine because the double arrow thing is going to extend that. I'll use some technology to make this look pretty though. So not really my best effort, but I think it'll work. You know, something like this. All right, here's a function notation equation, and that's okay. Remember, I mean, if you prefer to see it as y equals 6x, that's fine. Okay, and again, on this one, we'll see that the x-intercept and y-intercept are the same. So like I said, I would probably start with the x-intercept, even though in this format, I would probably even start with y-intercept if I was doing it by myself. But since maybe we're not used to that, I'm going to start with the x-intercept, okay? And that would mean then that the x value is the one we don't know. It's the y value one that we're replacing here with 0. So I get 0 equals 6x, and you can see just by dividing both sides here by 6 that I end up with x equals 0, okay? So that again, it would give us 0, 0, which is the origin, which is pretty easy to graph, right? It's right where the two axes come together. But what I would like here then is another point to put on this graph, okay? So just choose an easy value. So I'm looking at an ordered pair again. I would probably say, look, let's try where x is 1 and see what its corresponding y value is. Now, why am I choosing the x value? Because that's deliberate, by the way. It's because the operation is with the x. It's not with the x and y like it was on the last couple examples, I think. This one is just something times x will give you the y. Okay, well, let's replace the x then with 1 and see what happens. So I replace the x with 1. I see y equals 6 times 1. See how easy that's going to be? 6 times 1, boom, 6. So its corresponding y value here is 6. I get 1, 6. Again, that would make the original function or equation true. 1, 6, where is that? 1, 6, boom, right there. And then again, we're just going to use some technology to make this fairly easy for us. And then put some arrows on the ends of those lines to indicate they go on forever. And that would do it right there. All right, so here's our next example. And again, notice that the format of the function has changed. Whereas before we had the x's and y's on the same side of the equal sign, now it's just y equals negative 1/2 x minus 8. I know that's not a y, you guys. But remember, function notation f of x, that indicates that's the y value right there, all right? So the first thing I do on this, now I'm looking for the y-intercept. I'm not starting with the x-intercept. And again, the reason why that is because in this y-intercept, the x value is 0. Then I find a corresponding y value. That's because all the operations are with the x side of things. If they were with the y side of things, I'd choose a y value first. But this side, see how it's negative 1/2 times x, and then we'll subtract 8? That will give me a y directly. I can pretty much put this expression in the calculator and solve, okay? So right here, we can see with the y-intercept that it will replace the x value with 0, which I will do. So let's make that x is 0. So now we end up with negative 1/2 times 0 minus 8. And again, I'll just show this as y equals negative 1/2 times 0 minus 8. But remember, anything times 0 is just 0. So again, that's the important part here. What we get then is just y equals, remember, it's not just 8, it's negative 8 because of the minus sign right there. You have to be careful of that. So the corresponding y value when x is 0 is negative 8. So 0, negative 8 would be the y-intercept. That's important with this format, which we'll cover more in a later lesson. But 0, negative 8, I'll go and put that on the graph right now. It's about right there, okay? Now, I just need any other ordered pair. Any other ordered pair will do. And so I see I'm multiplying by a fraction here. I wouldn't want to choose a 1 in this case because it's going to keep a fraction in the answer. I don't want that. What I'd like to do is get rid of that fraction. So see how the denominator is a 2? I just need to multiply this by any multiple of 2, and that will essentially get rid of that denominator. So you could say replace your x with a 2, a 4, a 6, or an 8, or so forth. I mean, we want it to fit on the graph, but anything will do. I'm going to just start with the lowest one, which is 2. So you can see here in the equation, I'm going to now replace the x with 2. This will require a little bit more work than the y-intercept was. But by replacing that with 2, negative 1/2 times 2, yeah, see I get negative 1 right there. And then I will subtract 8. Just put that in the calculator, and that will tell you the corresponding y value here is negative 9. So 2 and negative 9, that'll fit on the graph. If it didn't, then I would have to go back and see what I need to do. But 2, negative 9, where is that? 2, negative 9, about right there. Now, some of you may be using slope at this point. We haven't gone over slope, so that's why I'm using this format. And yeah, some of you may even say, well, look, Sal, can I just put this into a table and then say 0, negative 8, and then 2, negative 9? Yeah, it's the same thing. It's just keeping track of their ordered pairs differently. But what we have right there is good enough to make the graph. And so however you do it, again, if you're doing it by hand, that should be enough. But, you know, I'm using electronics here, so it shouldn't be too bad to do something like this, okay? All right, here's this equation. Now, you'll notice in this equation that there's no x value, okay? So what I'm going to do is I'm going to solve this equation for y. This goes back to, I think it was 1.10, manipulating equations or solving literal equations. I want to solve this equation for y, and so in doing that, I don't want the minus 8 with the y, so I would have to say, look, let's just go ahead and add 8 to both sides and see what happens, okay? So that will drop the y. And then negative 8 plus 8, that's 0. And then 0 plus 8 is 8 right there. See how y equals 8? That's our actual equation. That's okay to have an equation like that because, and I'll do this with the table here, x and y. We can do a few values in this table, okay? The only value that will make this true is if you replace the y value with 8. So it doesn't matter where you are in the table. It doesn't matter what the x value is, I should say, in the table. The y value has to be 8 in order to make this true. So I just get a bunch of 8s like this. Now you just fill in whatever x value you want there. Maybe negative 10, maybe negative 5, 0, 7. It doesn't matter because the x value is not going to have any effect on this y value being 8 right there. So what does this look like? Well, negative 10, 8, well, that'd be up here. Negative 5, 8 up here. 0, 8, there's our y-intercept. And then 7, 8, yeah, about right there, okay? So what does the graph look like? It's really just, if you connect all those lines, all those points together to make this line, it's a horizontal line. And you'll see this, any y equals, if there's no x there, y equals just a number, you get a flat line like this, okay? And we'll contrast this with what x equals looks like on the next problem. This is a unique scenario, and you'll keep in mind that there's a situation where it's just y equals as well, okay? Again, if you make a table, it's always a nice strategy, although it's not always necessary, okay? What is this saying? Remember that we have to have only x values that make it true, right? So that means no matter what you do with the y, your x value has to be, in this case, a 9, right? So what would your y value be? Doesn't matter. 0, 1, negative 5,000. Doesn't matter, okay? Because as long as the x value is 9, it will be a true statement. The y value is not going to change anything right here. So what would this look like? Well, 9, 0 is right here, and then 9, 1 is right above it. And you could just, you could keep putting lines right there, but it's just a vertical line. Let's see if I can get the technology to work on this. That's okay. See that green line right there? So if you get x equals, you get a straight vertical line like this. If for some reason it was y equals, you'd have a horizontal line, okay, because it'd give you a y-intercept. Yeah, see, this is parallel with the y-axis, by the way. It has no y-intercept. So if you look for one on this one, you'd never find it. Same with horizontal lines. They have no x-intercepts, unless I guess it was the x-axis, but those are parallel to the x-axis, okay? Now let's just take a look at these graphs, just in relating it to what we saw in the last section. So remember, we would do some kind of vertical line test on these lines in order to see if it is a function, right? So I would scan this. See, I'm doing this one from right to left. You could say left to right, doesn't matter. But you see how that green line only goes through this purple line once? That would mean that this function that we have over here, and it is written in function notation, but it actually is a function because it does pass the vertical line test like we just showed right there. Well, what about this example as well? Remember, this is a flat line. Now, the look of the line is crucial, but it really comes down to this vertical line test that we do in order to determine if these are functions or not. So I take my purple line, I scan it. I like to scan from left to right, so you see how it's only going through that purple line once as I scan, either way, which means that this one also would be a function. Now what about this last example that we had? Well, let's go ahead and get ourselves a nice vertical line to test this with. And again, scanning, I like to scan from left to right. We won't actually make contact until we come to this line right here. But notice that this goes through the purple line in lots of different places. In fact, an infinite number of spots right here, if they're overlapping, which means that if you type in a 9 value for x into a machine, you'll never know what you're going to get out of this. I mean, there's an infinite number of values here. So this one does not pass the vertical line test, meaning that this one is not a function.